You know, there are ways of doing this differently than what I'm suggesting. If you're clever, you can look at this and say, okay, well, I know what this equation of the slope is, so I'm going to use this is my y values, my y1 and y2, and these are my x values. These are my inputs. But for the sake of doing something like what we'll do in 7, let's set up a table, n and t of n, where our sequences are always going to have an important term of 0 because that's going to give you part of the equation. And if we build it up to the 7th term, in this case here, 2, 3, 4, 5, 6, and 7, we can kind of fill in the stuff that we know. The 7th term is 205, and the 2nd term is 105. Well, there's an increase of 100 from here to here. Okay? There's an increase of 100. And we want to take that and divide it into 1, 2, 3, 4, 5 steps. Now we can count that out like I did, or we can recognize it from 2 up to 7. There's a growth of 5. And so if we take the 100, we divide by 5, that gives us 20. That is our incremental growth. You add 20 just to confirm. You got 125, 145, 165, 185, and then 205. That confirms. It's a good idea to make sure that it's working because sometimes we'll do something silly. We can catch it that way, which is nice. But then you can kind of take your steps back. And sometimes if you take a step back without confirming you've walked forward correctly, then you might run into trouble. So moving back, we're at 85, and then we're at 65. And here we're at our useful zone here. We know that it is increasing by a constant term because it's arithmetic. I didn't mention that earlier. And so arithmetic sequence, our initial value is 65, but we are adding 20 each time we increase by 1. So that's the equation we're looking at there. A geometric one then can be done roughly the same way. There's 0. Well, that's n then, and this is t of n. So I don't know what my 0 term is, but I'm not far from it here, right? The 15 is that term. And then 2, 3, and 4, it's not too far to go to get to 120. Well, this is slightly different. It's not a subtraction thing. I could say, well, you know, that was easy enough to look at, say 105 plus 100 is 205, or subtract the two, find the difference. I can't really just subtract these because this is geometric, which means I'm multiplying this by something 3 times to get me 120. So the opposite of multiplication would be division. If I take 120 and divide it by 15, I get a grand total of, I believe it's 8. I'm checking on the calculator now just to make sure since I'm talking to the masses here. It is in fact 8. Okay, I'm multiplying 15 by 8 to get to 120, but I'm doing that over the course of 1, 2, 3 steps. Well, that means 8 can be represented by something times itself, or another way of saying that, what is the cubed root of 8? Hopefully most of us know that what times what would give you 8 is going to be a 2. So 2 times 2 times 2 is 8. So we're multiplying this by 2. And again, to test it, to make sure that it's working, it's not just something you think might be right. Multiply by 2, you get 30. Multiply by 2, you get 60. Multiply by 2, you get 120. Confirmation complete. Now we just need to say, okay, what's our 0 term? Well, I multiplied by 2 this way. I'm going to divide by 2 to go back 1. And it is perfectly acceptable and almost encouraged. I would say leave it as a fraction. So that's a 15 over 2. It is a geometric sequence. So my initial value goes in front, 15 over 2, and what I'm doing each time is I'm multiplying by 2, raising it to the n power, and that's my geometric equation, or geometric sequence, arithmetic sequence.